We have learnt about standard lattice enthalpies, which give the enthalpy change when 1 mole of ionic lattice is formed from its gaseous ions under standard conditions. We can link lattice enthalpies to the enthalpy changes we observe when dissolving ionic solids in water. When an ionic solid dissolves in water, the ionic bonds within the lattice need to be broken, and new interactions/bonds are formed between the water molecules and the ions. Positively charged ions form interactions/bonds with the partial negative charges on the oxygen of the water molecules. Negatively charged ions form interactions/bonds with the partial positive charges on the hydrogen of the water molecules. During the process of dissolving ionic solids, therefore, we have ionic bonds being broken, which is endothermic, and interactions/bonds being formed with the water, which is exothermic, and the enthalpy change we observe is the summation of these two processes. The enthalpy change when 1 mole of solute/ionic solid dissolves in water under standard conditions is known as the standard enthalpy change of solution. When some ionic solids dissolve in water, the temperature increases, and the standard enthalpy change of solution is exothermic, which means energy is released by the system to the surroundings. For some ionic compounds, the standard enthalpy change of solution is endothermic, and we observe a temperature drop. Enthalpy changes of solution can be measured experimentally using a coffee cup calorimeter, where we dissolve a known number of moles of solute into a known mass of water and measure the temperature change. We cover how to perform the calculations to calculate the enthalpy changes from such experiments in Year 1. Let's construct a Born-Haber cycle that links together lattice enthalpy and the enthalpy change of solution for lithium chloride. On the left, we will start with the lattice enthalpy, which is the enthalpy change when 1 mole of ionic lattice is formed from its gaseous ions under standard conditions. Then we have the standard enthalpy change of solution, which is the enthalpy change when we dissolve 1 mole of solute in water under standard conditions. If we were to perform an experiment to determine the enthalpy change of solution for lithium chloride, we would find the temperature of the contents of the calorimeter would increase, and the change is exothermic, with a value of minus 37 kilojoules per mole. To complete our cycle, we need to know the enthalpy change in dissolving our gaseous ions in water under standard conditions. The enthalpy change when 1 mole of gaseous ions are dissolved in water under standard conditions is known as the standard enthalpy change of hydration. These values can be looked up in tables in chemistry databooks. The standard enthalpy change of hydration of the lithium 1+ ion is minus 520 kilojoules per mole, and the standard enthalpy change of hydration of the chloride ion is minus 338 kilojoules per mole. We can now calculate the standard lattice enthalpy for lithium chloride, since this is the one energy step we do not have a value for. Hess's law tells us that the sum of the enthalpy changes going clockwise equals the sum of the enthalpy changes going anticlockwise. We can now rearrange like this. We need to make the standard lattice enthalpy the subject, so we subtract minus 37 kilojoules per mole from both sides. If we plug these values, exactly as they are written here, into our calculator, we obtain a value of minus 821 kilojoules per mole for the standard lattice enthalpy of lithium chloride. If we compare this value for the standard lattice enthalpy of lithium chloride with the standard lattice enthalpies of sodium chloride, which is minus 769 kilojoules per mole, and potassium chloride, which is minus 698 kilojoules per mole, and if we now look at the size of the lithium, sodium and potassium ions, we see the smaller ions result in more exothermic lattice enthalpies. This is because smaller ions compact closer together in the lattice and thereby form stronger ionic bonds. If we think about it, the reverse of lattice enthalpy is the enthalpy change when we break the ionic bonds. Therefore, the more exothermic the lattice enthalpy, the stronger the ionic bonds. The size of charge on the ion also affects the lattice enthalpies, with greater charged ions creating stronger ionic bonds and therefore more exothermic lattice enthalpies. Similarly, the standard enthalpy change of hydration values are related to the size of the ion and the charge. The smaller the ion, the more exothermic the enthalpy change of hydration. This is because smaller ions are able to get closer to the water molecules and a stronger interaction/bond results. The greater the charge on the ions, the stronger the interaction with the water molecules, and the more exothermic the value for the standard enthalpy change of hydration.